So, as you may have heard, rumors has it that the processors are built from transistors. You can open up some Intel Pentium or Intel processor datasheet on the internet, and it will say that, for example, this processor has, I don't know, 2 trillion transistors, right? So you would think, okay, I take 2 trillion transistors, I put them in a box, I shake them, and then I have a CPU in my hands. Well, unfortunately, it's not true. All of these transistors are connected in certain ways, which we will study. And as we finish this subject, you will know everything about how each transistor is located inside the CPU. So to understand how CPUs work, we need to first study how the transistor works. So in modern days, all computers are made in this called CMOS technology, which is complementary metal oxide semiconductor technology. And all of these CPUs consist of N-channel and P-channel metal oxide semiconductor transistors, right? So you can write in a chat box how many of you know what is this N-channel and P-channel MOSFET. Metal oxide semiconductor field effect transistor, MOSFET. So many new words for some of you. So in the chat, how many of you know what these MOSFETs are? Quick. Those who don't know, those write in the chat that they don't know what it is. And those who know, those write that you know what it is. And if you don't write anything, then I assume that you're asleep or not even at the computer. Okay. Good. Then you will learn something new today. I read that almost nobody knows what, from what you write in the chat, I assume that nobody knows what this metal oxide semiconductor field effect transistor is. So we'll study it now. So this comes down to a little bit of chemistry, but you know, I'll talk it in simple terms. So basically, these scientists have discovered the following thing. There is this material called silicon with chemical, you know, symbol Si, maybe a bit bigger letters. And the silicon is group number 4 element in periodic table. I can maybe try to find periodic table in the internet, and here is one, and we can see silicon is right here. It's element number 14, and it is in the 4th group, and it is not a metallic element, from which we can make the following conclusion. If we would have a silicon atom, I'll try to, you know, copy this thing. So this is, oops. So silicon, okay. Silicon has 4 electrons, so I'll write inside +4. 4 electrons in its outer shell. Not enough space, maybe tiny text. Like this. So silicon has, since its number in periodic table is 14, right? It means that silicon has 14 electrons and 14 positrons inside the core, and electrons just wandering around. But in chemistry, we know that the closer the electrons are to the core, the harder it is for them to get out, right? So the first 10 electrons are very much connected to the core, and they're in these, special places around the core from which they cannot jump out. But outer 4 electrons, they are so far away from core that they can also wander around a little bit. For example, if we cool it to 0 degrees Kelvin, to absolute 0, they're of course all at the core and they aren't really doing anything. But if you heat the material up, they start to wander around. And the next thing is that silicon is non-metallic, so it holds together with other silicon atoms using this so-called covalent bond, which means the following thing. Silicon makes a crystal lattice. I draw it in 2 dimensions. It's actually more like triangles in 4 dimensions. So each silicon is connected with using an electron to its neighbors. So for example, this central silicon, it has 4 free electrons, and they are used to form the covalent bond and to hold this material together. Without this bond, it would be just, individual atoms. But if you take poor silicon, each silicon has 4 free electrons, which are used to connect to its neighboring silicon atoms. And this covalent bond holds this material together. So, I don't know, this central silicon, it is connected to its neighbor using 1 electron, the second, the third, and the fourth. So it cannot, for example, connect to the 5th atom. So it's connected to its neighbors. And this silicon, for example, is connected to 1 neighbor, to the second, and to some other, like this, okay? And this is pure silicon material holding together. And this second silicon is using his second electron to connect back to its neighbor. And here also, so you actually would see 2 electrons in each of these connections. So one comes from 1 atom and the other comes from the other atom, and so on. Okay, and the thing is that pure silicon is not actually very good at transmitting electricity. So ideally, at absolute 0 temperature, these electrons are only used for this bond. They basically circle around in like a number 8 shape around 2 electrons, around 2 cores, and hold them together, right? So each of these electrons is just traveling like this and holding these atoms together. And the second one, a little bit different angle, but doing the same. But as we heat up this material, some electrons, they heat up so much that they jump out of this bond and they start to wander around this lattice. But after some time, they get tired and they fall back into some free bond place. But some other electron heats up and also jumps out of its place, wanders around a little bit, and then falls back. And the number of electrons which are wandering around is just proportional to temperature. You heat this material up more, more of these electrons have enough energy to jump off their place and start wandering around. And this is the reason why if you heat up a semiconductor, it actually becomes a better conducting material. Up until some 600 degrees Celsius, well, all of these electrons have been heated up so much that they jump off of their bonds and they all travel around, and there's no more electrons to be heated up, energized. And then this thing becomes something like metal where you heat it up more And then because these atoms also have some thermal movement, they actually start to bother electrons from moving around. They keep bumping into the core and in atom cores, and it starts to become worse conductor. But generally, if we, I don't know, I'll put here temperature, and I mean absolute 0 kelvins here, and then resistance. I'll just draw this R. So if you heat up this material, it from absolute infinity, oh, actually resistance is a bit opposite, but it's G will be electricity conductivity. It goes up and then it kind of stops and starts to go down. But we are maybe somewhere here. Is room temperature 25 degrees Celsius. It's 272 kelvins, right? So if we heat up the material to something like 200 degrees, it actually starts to conduct better. Okay, so for this reason, this material is called semiconductor. So one word of this long text we have figured out. Semiconductor is basically, you can just think of it as silicon. Silicon is the semiconductor, and you know, it's not good conductor, it's not bad conductor. It conducts a little bit of electricity. Okay, so and now we need to talk about these N-channel and P-channel stuff. So semiconductor by itself is not great at conducting electricity, but I don't know how, but in something like 60s, people had this wonderful idea. Why don't we put some other material which has either one more or one less free electron? We put them on this silicon, we heat it up so that this material melts into the silicon, and you know, and maybe we get some different result. So in chemistry, oftentimes people use boron and gallium and maybe indium as this material which has one less electron, and for example phosphor as one that has one more electron. So let's use phosphor. Let's say that somebody decides for whatever reason that they will put phosphor atoms P. So, or maybe I'll write it with text. P size 20. So phosphor has yes, so somebody asked, isn't it silicium? It's a good question. How do you pronounce it? Let's see. I just, God damn it. Stupid history. Let's see. How do you call this thing? I don't know if I can pronounce it that way. I don't know. The English. Well, it says here the element is silicon, but in different languages, in Latvian language, it's called silicis. So if you're saying, isn't it silicium? In your language, probably, in my language also, but in English language, it's kind of called silicon. Silicon. Okay, let's see. P phosphorus. Okay, phosphorus is a chemical element with symbol P. Okay, so I'll call it phosphorus. And then its atomic number is 15, so it has 15 electrons. only 5 of them are in outer shell and can make covalent bonds. So P, I'll write 5 plus. Okay, maybe a little bit smaller letters. So phosphorus and 5 plus, like this. So our little friend phosphorus has 5 electrons. And what people had decided to do, I don't know why, I wasn't born yet, but they decided that they're going to dope pure silicon with phosphorus atoms. So how it's done, as I mentioned, they take this silicon, pure silicon, and then they put piece of pure phosphorus on top of the bulk of silicon, and then they heat this thing up to 1200 degrees, and the temperature is too low to melt this material, but high enough to make these silicon atoms in the lattice oscillate so much that these phosphorus atoms kind of just jump in to some place of silicon. Some silicon moves aside or expands to the up or to sideways, and some phosphorus atoms kind of just randomly fall into this lattice, and they start to pretend that they are silicon, right? They also make the same covalent bond. They have 5 electrons, so 4 of them make this covalent bond. And what happens is also that each one of these phosphorus atoms also produces 1 extra electron. As you can see, they have 5 electrons. 4 of them are in the covalent bond, but this 1 electron kind of just wanders around all the time. So we have 1 extra electron. So this thing actually becomes a bit better conductor because it has this 1 extra electron wandering around. Again, you freeze this piece of material to 0 kelvins, the electron is only circulating around the core and doesn't conduct electricity. But if you heat it up to room temperature, for example, it's hot enough for this electron to be almost all the time wandering around in the lattice, okay? And this way, because we have 1 extra electron, if we put something from 5th group of elements in this material, we get N material, okay? So I don't know, maybe I'll write it somewhere here. Add group 5 element, get N type semiconductor. Okay. And also the scientists decided that they want to experiment some more, and they want to also put a 3rd group element into this mix. Often it's gallium. Let's see, English. G-A-L-I-A-M. Gallium. It's called Ga. Its atomic number is 31. Again, it only has 3 electrons in its outer shell. This is why it's group number 3. Group number 3. 1, 2. This is a bad numbering. Too smart for me. Let's find a good. Oh, this is old school. This is good. So this is group 3A. So for example, gallium, I don't know. I think because gallium is kind of common metal. So what happens if instead of using phosphorus, we will use gallium? So gallium has only +3 electrons, and its name is Ga 20. Oops. So gallium has only three free electrons in its outer shell. So what happens when we dope this thing into the silicon? So let's imagine that we didn't have phosphorus here, just silicon. The same thing, we put a piece of gallium on top of this silicon bulk. We also, basically what people do is they weight this silicon material, then they weight this gallium, and they know the mass, they know the atomic weight, and they calculate how many atoms are in this gallium, so they can kind of control how many gallium atoms will diffuse into this material and replace some silicon atoms. Okay, and it can also be simulated in the computer. And actually, one of my classmates from a secondary school is working in Germany, calculating these diffusion things and simulating them. So when you heat this material up, of course, initially there's high concentration of this material at the top, but then you heat it some more and then it diffuses all over this material, and it's relatively thin, so it happens pretty fast and it can be simulated with computers. So what happens if we put gallium, which has one less electron than we need, in this crystal lattice? What happens is basically all the time there is lack of one electron. Okay, so gallium makes, three ways. It has double covalent bond, but in one of these connections, one electron is missing, right? So we could say this bond is a little bit worse than the previous one. But what happens is, it turns out, well, you would think that, for example, this material doesn't conduct electricity because there's no free electrons. But what happens is, if you heat this material up, to room temperature or something like that, and you put some voltage across it, what happens is basically some electron gets this heat energy high enough that it just jumps from one bond to the neighboring bond. And this is how electron moved. So electricity was conducted, and in modern days it's assumed that electricity goes from plus to minus, but electrons go the opposite direction. So basically electricity was conducted because electron jumped from one bond to the neighboring bond, and so on. Maybe it wasn't such a good example. I'll put it back here and I'll show it a bit differently, maybe like this. So transparent selection. So, as I mentioned, for example, here we lack one electron, but we put some voltage, we solder some wires to the sides of this material, and we put a battery with plus and minus across it. So let's say we have a plus voltage here and minus voltage here. And what happens is the electron jumps from one bond to the next one. So this thing moved, and the next electron jumps from a previous location to the next, like this. And again, electricity was conducted, and so on. And this happens all the time. But generally, P P material is worse in conductivity because you need to do this extra work. Electrons are not wandering around in this crystal lattice, but they have to kind of move from bond by bond. And these places which lack this electron are called holes. I will write P and plus here. But, you know, it's like here is a hole and it's kind of static. It isn't wandering around. You know, when the material is heated up, these electrons can spontaneously jump around within the material. So, you know, it's not locked in. It moves a little bit. Only when you apply voltage, it moves in certain direction and moves the electricity. This is the electricity movement, and it conducts. But generally, this is how this other material works. So these are holes. I'll just write it down in the text. Hole, lack of electron. Okay, like this. So I'll write also down here in text that if you add group 3 element, you get P-type semiconductor. So semiconductor because it's not great at conductivity, it's not bad, but it's not great. And you can create P and N type semiconductors by adding or removing, by adding fifth or third group element. So this is how we get them, and without really going into some deeper details, I'll just tell you one thing. I don't know how people discovered it. It's pretty amazing, but they discovered the following thing. If you take P-type and N-type material and put them side by side, I'll just write it here. Here's, for example, P, and here is N-type material. You can do it, for example, by injecting gallium from one end and phosphorus from the other end, and then when they diffuse, you'll get half of this thing as P and the other half as N. But basically, you can construct a material where you have P and N side by side. And what the scientists found out is at this region, holes and electrons kind of recombine. All of the free electrons are caught into these holes, and you have a region that doesn't conduct electricity at all. But it starts to conduct electricity if you put it from P to N, so you can have some wires connected here. And if you put here plus and on the opposite end minus, electricity can flow. But if you put it the other way around, it doesn't flow. So this is why it's called also semiconductor, because on one way it conducts electricity and to the opposite way it doesn't. Why? As I mentioned, holes and electrons recombine and all electrons are caught by all holes. There's no free carrier running around. So this region where they meet, it basically becomes total insulator. So if you put more holes in this P region, they are not compensated by the electrons and the electricity can start to flow again. But if you put it the other way around, you only recombine more electrons with more holes, they disappear and it doesn't conduct the other way around. 1 second. So this is how this material works. And now, finally, we can move to how we can build a transistor. So I'll immediately just tell you that transistors can be N-channel or P-channel because we have these two ways. Metal oxide we will do a little bit later. Semiconductor is here. Field effect I'll show you in 1 second. So basically, what people want to do is they want to make something similar to PN, but something that you can control, right? So this PN junction is very popular. It's called diode. I can even write it over here. Simple diode. See. You know, just basic diode. I'll just write diode. Diode because it, you know, conducts in one direction and doesn't conduct the other direction. And so now we want to build a transistor. And what people figured out is you can do it in the following way. Basically, what we want to build, I'll just draw it like a box, is we want to have some cables. And we want to build them as a switch, which is switched off. And then with a third cable, we can turn on this switch, like connect it, and the electricity flows. And if we remove this control signal, the electricity is switched off and it doesn't conduct. And it can be easily done with a transistor in the following way, which scientists discovered in 1960s. I think it was when the first transistor was, field effect transistor was displayed, and they do it in the following way. They make two pockets. Sorry, I'll start with the material. So first of all, we take pure silicon, and then we lightly dope it with, for example, gallium, and we get P-type material. This entire material is P-type. So P-type. Okay, so this material P-type with lots of gallium, with some holes in it, and that's it. Next thing is we take a fifth group element like phosphorus, and we strongly dope some two regions right here, one pocket and the other pocket. And because we put, for example, 2 times more phosphorus than we put gallium, phosphorus is 2 times more here than gallium. So it from P-type turns into N-type. And we write this N and we add a little plus, which means heavily doped N. Or was it minus? I don't know. But generally, initially it was all P, but we just added so much phosphorus in this region that phosphorus overruled gallium, and it becomes N regions, 2 N regions. So now, if we put here some copper, and also here some copper, which conducts electricity, some copper wires, and we put plus here and minus here, does it conduct electricity? So if you remember from diode, electricity can be conducted from P to N, but it cannot be conducted from N to P. So right now this thing doesn't work. It doesn't conduct electricity either way because it's N to P doesn't conduct. And even if we change the polarity, from N to P, it still doesn't conduct. From material to out, it would, but the other way it doesn't. So next thing that we want to do is, so basically the idea is the following. If we could attract lots of electrons to this place, here would be N. This region would also be lots of electrons, so they would overrule this P-type material property, and we would conduct the electricity over this channel. and we would be able to conduct electricity. And if we push these electrons back inside the material, it would stop conducting. And basically it's done in the following way. With a laser, you can oxidize this part of material so that it becomes oxide, silicon oxide, like sand. Sand doesn't conduct electricity. So you get some insulation here. And then you simply put a third piece of copper right here. Right. And the fourth part is here. Fourth electrode is here. So basically, what happens is we will call this thing gate. Has nothing to do with Microsoft founder Bill Gates. It's just called gate, much longer than that. And this we will call bulk or wafer. So basically what happens, you know from your, I don't know, primary school that plus positive voltage attracts negative voltage, the opposites attract. So if we put positive voltage on gate and negative voltage on the bulk, the electrons that are inside this p-type material, they get repelled by this minus, they are pushed away and they are attracted to this positive gate. So electrons run to this location. There are so many electrons that they overrule the p-type material. This material starts to look like n-type. Temporarily, and electricity starts to flow from one pocket through this channel to the other, and basically we have a transistor. And you have to remember, electricity can be conducted one way or the other, it doesn't matter. Transistors are unipolar devices, they don't care which way the electricity goes, it just goes that way. And if we, for example, remove positive voltage from gate and negative from bulk, these electrons, they have no business to be hanging around here, this channel anymore. So they just go throughout all of this material due to their thermal movement, random movement in the, in the material, and the channel disappears and this thing stops conducting. So it doesn't conduct any electricity anymore. So yeah, I'll delete this one and this one. And then this is how we can switch off the transistor. If we apply voltage between gate and bulk, then electricity flows from one pocket to the other or back. And if we switch off this voltage between gate and bulk, then electricity cannot move anymore, it's stopped. So we have built a switch basically. So, and if we go back to the name of this thing, it is N channel or P channel. So if we swap material type to N and pockets to P and gate voltage to negative and bulk voltage to positive, we can also build a transistor like opposite transistor, P channel transistor. Next is metal oxide. So the oxide is the thing that protects gate from this current that was flowing from one pocket to the other. So this is the oxide. Metal is here, here, and here, and here. semiconductor is this whole material, and field effect is, field effect is that if you put plus somewhere, it attracts minuses, and if you put minus somewhere, it attracts pluses. And so it's, electric field, basic, physics. And transistor is when you build it this way. Okay, so this is how transistor is built and how it works. And one more thing, bulk is always connected to one of the pockets like this, because it's just easier to construct schematics with this type of connection. So bulk is, and as a result, the transistor actually has only 3 wires because the 4th wire is internally connected to one of these 3 wires. And these wires will have the following names. So the wire to which bulk is connected will always be called source, because electricity will be mainly flowing out of it. Source. And the other wire, since electricity will mostly be flowing into it because of some things in the schematics, it is called drain. Okay, and so generally transistors have drain, gate, and source. Bulk is also there, but it's connected to source internally. So you get a transistor with just 3 wires. And now I will also draw you a schematic symbol of transistor. So transistor in schematics looks like this. So we have one pocket, bulk, and another pocket. From pockets, cables go out. We also have insulated gate, so it doesn't touch these parts. And bulk is connected to source. And then there's also a small arrow which shows which type of transistor it is. Is it a P or N channel? So P type material needs to be turned N to start conducting from N pockets through N region to the second pocket. So this will be called N channel. What I have drawn here is N channel. P substrate, and then inside this P you can make a region N and start conducting, or switch it off, then it becomes back P and doesn't conduct. Transistors by default don't conduct, only if you apply voltage then they start to conduct. And so this is called N channel, and diode is drawn like this from P to N, because it conducts from P to N, it's an arrow, but because it doesn't conduct from N to P, it's a block here. And the same inside the MOSFET. If we have P material and N channel, then the arrow goes this way. So this is the schematic symbol of N channel MOSFET. And you could go online and buy them if you want. Okay, so this is how it's built. And one more thing. Here's the problem. Initially, I promised you that this transistor conducts both ways or can be switched off both ways. It was true if the bulk wasn't connected to source, but here's the problem. If you put voltage in the opposite direction, for example, plus here and minus here, even if the gate is switched off and there's no channel, the problem is that electricity goes into this pocket. Here's N, here's P. From N to P, it doesn't move, so electricity cannot flow further. But since bulk is connected to source, electricity flows through the bulk, and here is P and here's N, and from P to N it can go, and so it goes here and flows like in short circuit. So unfortunately, transistors, they don't conduct electricity from drain to source, but from source to drain, they always conduct it. And a proper schematic symbol will also have this reverse diode visible, so that you don't forget about it. If you ever draw a circuit, full transistor schematic symbol is this, because the moment we connected source to bulk, here is P and diode in in this region. Here is P and junction, P and diode. So transistors don't conduct electricity one direction, but conduct it the other way. Okay, so Matthew is asking, I guess that MOSFET P and P is working the other way. No, you mean P channel MOSFET? Yes, so P channel MOSFET works kind of the same way, but the other way around. So I don't know, maybe we don't have enough time to go through it. And maybe also, since you're more of, not so much into electronics, then maybe we don't have time for it. Maybe we do. But generally, okay, I'll just quickly draw it. So P channel MOSFETs are totally the same principle as N channel MOSFETs. It's just everything is the other way around. So material was P. Now we are using N type bulk. So initially we doped this material, this pure silicon, with N-type material, something like phosphorus. It has lots of free electrons, but then these pockets we dope with, for example, 2 times more borons, so that this becomes P and heavily doped, so heavily doped that it overrules the N-type that was originally there. And now we have a, P pocket, N material, and P pocket. If we connect cables like this, and we put voltage plus here and minus here, from P to N, it could flow. The electricity comes here, but it cannot flow from N to P, so it stops, so it doesn't conduct. And again, we introduce some insulator. We can just oxidize the same silicon that is the material. We just, point some laser at it and burn it a little bit. It becomes silicon oxide, which is sand, which doesn't conduct electricity. And then we put this gate, copper. And here, what we have to do, I'll also draw the bulk. So this is N-type region with lots of electrons, but for this region to become P-like, we need to push the electrons away and attract lack of electrons, or some missing electrons, which would be holes. So to push away electrons, we now need to put negative polarity here and positive polarity here, the other way around again. So electrons don't like negative polarity, but they love plus, they love positive polarity. So electrons from this material run away to bulk. And since they have deserted this region, it becomes somewhat positively charged. Even electrons that, some electrons just jump out of the cores and run to this other end of the material. And so some ions of material stripped from electrons stay there, they are charged positive. And so you get positive region here. Some electrons jump out of their atoms, run away, and the atom stays positively charged. And so you get positive region here. And electricity can go from P to plus and back to P and flow through. So now electricity comes here and it moves through. And if we remove, for example, the voltage between gate and bulk, then electrons go back into their places, this region disappears, and electricity is not conducted anymore. So we can switch on and off the channels by putting voltage on gate. So again, this is called gate. And for P-channel transistors, bulk is connected to the other end. It doesn't matter because you can just rotate it, but for sake of simplicity, bulk is connected to the other electrode. And so this will now be called source, because definition is bulk is connected to source. So however we draw it, source is the one that bulk is connected to. And this will be called drain. And unfortunately, since electricity is flowing this way, then for P-channel Mosfets, drain current is given in data sheets as negative with minus sign. I don't like it, but this is the way it's done. And so I'll just write it down here. So this is P-channel. So because channel is created, it has to be the opposite of the bulk material. Okay, so now source, gate, drain. Bulk is hidden from us because it's internally connected. So I'll draw the schematic symbol for P channel MOSFET, and it is like this. So again, we have one pocket, bulk, the second pocket. Well, the bulk should be in the opposite way, but it's drawn in this way. Now the bulk is connected to the upper pocket. Gate is still insulated, and because it's N-type material and P-type channel, and we draw arrow from P channel to N material, the arrow is the opposite way, like this. And there's this body diode again. So from P to N, electricity can flow. If we put a reverse voltage, if we put plus here and minus here, if somebody just connects them the other way around by mistake or something, so electricity can go from P to N. It cannot go from N to P, but it can go through this bulk electrode here. So again, this transistor also has a reverse body diode, so you cannot actually connect it the opposite way, unfortunately. So this is the schematic symbol of, whoops. Okay, I need to press Control to copy. So this is P channel MOSFET, right? And you have to be careful about these things, because in schematics, there's no law that is requiring that I have drawn this thing exactly this way, right? I can, for example, inside the schematic, I can, for example, mirror this thing if it's convenient. So how do I mirror it? Flip horizontal, flip vertical. Yeah, flip horizontal. For example, when I draw a schematic, I can, flip it the other way around. I can also mirror it vertically. And so this thing can actually become very similar to this N-channel MOSFET. So the only thing that determines whether this is a P or N-channel MOSFET is this arrow in the center. Oops. So this is why it always needs to be drawn so that there's no mistake about which kind of transistor it is. So for P-channel transistors from P center channel to N material, it's outwards because channel is formed here. And for N-channel MOSFETs from P material to N-channel, channel is formed here when it's open. So it's showing to the N from P to N. And this arrow is the one that determines what kind of transistor it is, not rotation or something like that. I think I haven't translated the tests yet, but for Latvian students, I take this transistor, I copy it 5 times. Sometimes for some copy, I rotate it, for some copy, I mirror it, and then people need to say which type of transistor it is. Is it P channel or N channel? And the only thing that determines it is the arrow here. Okay, so this is our transistor. This is how it works. And to make this thing complete, I have to also give you some circuit as an example of how this transistor works. So you just have to remember that N-channel MOSFETs are turned on with positive voltage on gate because they need to attract negative electrons to form this channel. So this MOSFET will always be on the lower side of the schematic. And the load that you want to turn on is on the upper side. So let's say I want to turn on this light bulb with some 5 volts. To do it with N-channel MOSFET, I put it in the bottom part between the light bulb and the ground. MOSFET is like this, P substrate N channel, so arrow goes like this. And here is 0 volts, right? So 5 volts, I don't know, maybe it's a battery or something like that. So if I connect gate to 0 volts, there's no voltage between bulk and gate. So the channel is discharged and it doesn't conduct electricity. So I would delete these light, drawings. But if I do the opposite, if I connect with some switch or something like that, if I connect gate to positive voltage, gate is charged positive, bulk is negative, so gate with its positivity attracts negative charges, and N channel is formed and electricity starts to flow through and the light bulb starts to shine, right? Because here in the gate we had to put plus to attract minus. So N channel MOSFET is like this, and I'll draw this body diode just in case, because it's the right thing to do. So N-channel MOSFET, you set gate high, it turns on, conducts electricity. You set gate low, it switches off, doesn't conduct electricity. I'll write it with text here, actually. So So I didn't write negative voltage because you don't have to put some -5 volts on the gate. You just have to disconnect it from the positive voltage and connect it to ground, to 0 volts. Also, one important thing, here's the problem. If you connect a transistor to 5 volts, you open it, right? Electrons run to gate. Gate is actually charged positive to attract these, you enforce gate to be positive, and the channel then is attracted negative. I'll also draw it here. And the thing is, you get a tiny capacitor here. And if you only just disconnect the gate from 5 volts, but don't connect it to 0, this charge stays here and transistor stays open, right? So you have to connect it strongly either to 5 volts or to 0 volts to discharge this charge. Otherwise, there's still some charge. Yes, it disappears over time into air, but this transistor stays semi-open, and this light bulb kind of shines a little bit, and this transistor can actually get damaged because if it's half open, half closed, then all the power is on it. It's not 0 volts, it's not infinity resistance. It just starts to heat. So you have to connect it either to 5 volts or to 0 volts to shut it. Okay, and the same small schematic for our P-channel MOSFET. For P-channel MOSFET, you always connect it on the top of the load. You use it if you must have the load grounded. So for example, a good example would be you want to turn on some electric motor, right? Motor. But for safety reasons, the motor's chassis is connected to ground to absorb some, electromagnetic shock and something like that. So one of its sides, for example, internally with this cable, is already connected to ground. You cannot connect it in the upper part here, because then you will have some short circuit from plus to chassis to ground, and it will just break everything. So you have to switch it on and off in the upper part of the schematic. Maybe I'll move it a little bit down. And this is the case where you use P-channel MOSFETs. So P-channel MOSFET has to be connected in the upper part of the load, like this, body diode going here. And here I will connect my 5 volts. And here is 0 volts. Now, so what you need to do now to turn on this P-channel MOSFET is you need to attract pluses to the channel. You can do it with minuses. So in this case, you connect gate to 0 volts to charge it negative. And the bulk is connected, hard-coded, connected to 5 volts, so it will charge positive. And this is the reason why you don't need, -5 volts to open this transistor, because this bulk, this material, is already connected internally to 5 volts, and you just set it lower than 5, and it will be relatively positive while this gate is relatively negative. So the gate is, the channel is formed and it starts to conduct electricity. And to switch this thing off, you disconnect it from 0 volts, you connect it, oops, you connect it back to 5 volts. And since in this case, gate and bulk has the same voltage, these minuses run to the pluses, they recombine, destroy each other, you know, love destroys, and channel disappears and it doesn't conduct electricity anymore. Okay, so I'll write it with words. P channel MOSFET is connected between supply and load and turned on with ground voltage and turned off with supply voltage, like this. You know, they're kind of like opposites. So P channel you put in the upper part of the schematic, you turn it off by connecting to 5 volts and turn on by connecting to 0 volts. You know, so this is how these transistors work. And, you know, basically, this is how they work also in the computers. And in next lesson, we will connect these P channel MOSFETs and N channel MOSFETs in one special way, which will start to do some arithmetics for us. It will be pretty interesting. So this is basically all about this chemistry stuff, about this material stuff. It will never happen again. Don't worry. If you didn't understand anything, it's, you know, it's fine. Yeah, but this is the physics part of this, how the transistors work. Now you can ask some questions, and also you can write in chat, honestly, did you understand anything or did you not understand anything at all? Time for questions, because it's 11:53, so we kind of have to end this interesting lesson. So now it's time for your questions. If you have no questions, you can also, you know, disconnect if you have some business to run to. So your questions now. Don't be afraid. There's no stupid questions. So you're asking about video lectures.